Silence! All right, it's working. Okay, so anyway. Yeah, you do get to sleep in. It is a 3-day weekend. So yeah, more time to do math homework instead of math lessons, right? I know that the guys who are in Aspen skiing right now, I know they're at the top of the slope watching the videos on Corpus Road before they go down, because I told them to do that.
Like one video, one.
Right, that's right. Yeah, watch one video or do at least one example and then ski down. Come back up, watch another video, ski down. Yeah, okay. So we are on example 6. Now, before I do that, let's come right here and let's regurgitate the formula for the linear velocity of a spinning object. We call the linear velocity V, okay? And what is it? The linear velocity of a spinning object. It's directly proportional to the radius by way of the constant, which is how fast it's spinning, which is, thank you, omega. V equals R omega. You got to memorize that. V equals R omega. Omega, remember, is theta per time, because that's angular velocity. Linear velocity in general is distance per time, okay? But we derived it up here kind of in sequence, and so we get R omega. That's the one you're going to be using. V equals R omega, V equals R omega, V equals R omega. Okay, let's look at example 6. It says to determine the angular velocity, that's going to be omega, in radians per second. So we talked about it yesterday. There are lots of different ways to represent angular velocity. You could do revolutions per minute, like your tachometer in your car. You can do rotations per second. You could do degrees per day. You could do cycles per second. It's telling us here that we want it in radians per second. So that unit will be specified. And the linear velocity in inches per second, okay, of the tip of the second hand of a clock that's 5 inches long. All right, so we kind of had an experience with the clock yesterday. This one is going to be the second hand, not the minute hand, not the hour hand. So let's just draw the second hand, and there's the length, okay? So what we need to do is, it says to figure out the angular velocity. Well, if you can come up with any angular velocity in any units, we can convert it to radians per second, okay? So what do you know about a second hand? Remember, angular velocity is rotations per time. So let's think about it. The second hand makes one rotation every minute. Okay, good. Every 1 minute. All right, so there's a good place to start. One rotation per 1 minute. Now that we have some type of angular velocity, let's stoichiometrically, ooh, that's a good adverb, convert it to radians per second. So let's go ahead and do the time first. I have minutes down there, so I'm going to put minutes up here. I want seconds to appear, so I'll do that. What's the conversion? 1 minute and 60 seconds, and notice your minutes divide out. Now, you could have gone straight to one rotation per 60 seconds, right? The second hand makes one rotation every 60 seconds. That would have been fine. That would have saved you one conversion factor, right? But if you don't, that's okay too. Okay? Just dimensional analysis. Multiply by fractions equivalent to 1. All right, so now we have seconds where we want it. We need to get rid of rotations and convert it to radians. So here we go. Rotations is in the top, so we need to put it in the bottom. And we want radians to appear, so we'll put it up there. And now we just think about what the conversion is. One rotation is how many radians? 2 pi. Good. And then you can divide out your rotations. And now we have units of radians in the numerator and units of seconds in the denominator. Radians per second, that's what we want. And so now we know 100% that this is the correct, that's going to give us the correct number, all right? So notice we don't have to worry about the ones, multiplying or dividing. So really it's just going to be 2 pi divided by 60, right? 2 pi divided by 60. So let's do that. 2 pi divided by 60. You don't need 2 pi in parentheses because they're being multiplied, bless you, in the numerator, bless you. You're welcome. So there you go. Omega, angular velocity is, you could push the lid down on the back and it'll lock in. Yeah, it's you didn't break it. The custodian takes the lid off every day and doesn't snap it back on in the back, on the hinges. Okay, so I'm going to put, again, I'm truncating, so I'm going to put 104, and then I'm going to put units of rads per second. Now, we do need to put rads in this case. Remember, radians are just a description, because if you didn't put rads per second, you would just have some blank per second, right? And that just looks funny, blank per second. So if it's an angle, you don't need to write radians, but so that it makes sense, radians per second, go ahead and write rads. Now, do you think I might ever have to use that number again? Probably so, right? Because it asked me for the linear velocity, and I know that that's part of the linear velocity equation. So if I know that this decimal answer goes on and on and on, but I've only reported 3, I'm going to store it. So again, people are reluctant to store, but you got the whole alphabet here. So stow is right above on. If you just hit stow, it's going to bring up the answer from the previous line. Answer, arrow means store as, and you can pick any letter you want. I would stay away from X, simply because it stores things default to X when you're in your graphing window. I like alpha, and then right below alpha, right below is A. That's why I like it, alpha A. Hit enter to lock it in, and boom, there it is. Now, little tip, if you stored it as A on your calculator, as a reminder, I don't care if you come over here and call that capital A. That's fine, okay? It's a reminder. Use the live answer. If you want to put ... at the end of your 3 decimal approximation, there's calculators under desks, yeah. Oh, yeah, I'm gonna, instead of putting them back in the box, you can just start putting them under your desk, okay? All right? And if you don't have one, there's some over here. All right, I'm still trying to find batteries to power up all the rest of them, but we should have enough. Okay, so there's the first part. Now it says find the linear velocity. This is an object that's spinning, right? The second hand is spinning around. So linear velocity is what? What's the formula? R times omega. Yeah. All right, so let's plug in. The linear velocity V is, what's the radius of the second hand? 5. And again, I'm going to put units here just to make sure I'm doing it right. Dimensional analysis. 5 inches times my angular velocity, which was 0.104. 0.104 ... radians per second. Now, before you pick up the calculator, think about what your units are going to end up being. What is inches times radians? Inches. Good. So this ends up being inches per second. Is that what we wanted in? Yes. So again, when the units work out, you know you have the right calculation. So back to the calculator, all I got to do now is go 5 times alpha A. Now, we didn't really need to store it because it was in the previous line. You could have just hit times 5 and it would have recalled it. But you never know. You never know when you're going to need it. So get in the habit of storing things. And it's 0.523. Okay? 0.523 inches per second. All right? There we go. Inches per second. So how exciting. And this is for all clocks, right? For all clocks, they spin at the same angular velocity, but depending on how far out you are from the center, if you were riding on the end of that second hand, you might experience a different kind of thrill, right? So if there was like a snail that was taped onto the end of that second hand, 5 inches from the center, that snail would be traveling around a circular path at a little more than a ½ inch per second. I think that snail would be saying what? How did I get here? If it had hands, it would be throwing them up. or holding on, right? We taped him down, but he still probably would hold on, right? A little more than 1/2 inches per second. That's pretty cool if you're small. That's pretty fast, right? Okay, good. All right, speaking of taping things down, I alluded to this yesterday. So I grew up in the LP and the record era where we had albums. I told you about that. And so I spent a lot of time just listening to records. And I got bored. We moved around a lot, so it was always hard meeting friends. So I just kind of, and I had a little brother who I used to beat up all the time, so he didn't want to play with me either. And my older sister, she was trying to like dress me up in leotards and play dolls, so I didn't play with her either. So I spent a lot of time just like listening to records. And when I got bored, I would do this. I literally would do this. So this is not just me saying that I'm doing. I actually did this. Okay, I taped ants down to the record player. I did. Okay, we used to. This is when I lived in Laredo, Texas. Okay, Laredo, Texas. There's not much to do in Laredo, Texas. We had these gigantic. They were like bullet ants, but they were gigantic ants that they were all over the place. So I would get them, and I would get Scotch tape, the clear transparent tape, and I would tape them down to records, see if I can make them dizzy and release some of their formic acid. Okay, so I'm taping down ants to a 12-inch diameter LP. LP is a standard word for a record. It means long play. So that's like a full album, like 10 songs at least, 12 songs sometimes. That's long play. It's a vinyl record to spin on his record player. We didn't call it a turntable. It was just a record player. They also have records that are called EPs. Do y'all know what that stands for?
Something play.
Yeah, good. Something play. Extended play. Okay? And an extended play is usually, it's like 5 to 6 songs. It's not quite a full album. Like Cody Johnson right now in 2018 has like a 5-song EP that he's released on Spotify. Okay? It's just like, I made some songs. It's not enough for a full album, but I want to get it out there, so let's release an EP. Okay. So anyway, LP is the long play. You had to play them at 78 RPMs. For them to sound right, you had to play them at 78 RPMs. I told you the other day that we also had 33 1/3 RPMs, and that was for the bigger singles. They were smaller, but they had a larger hole in the middle. Okay, so what is the linear velocity in feet per minute of the ants that are taped down at the following distances from the center of the record? Okay, so let's draw a picture here. All right, here's the center. The LPs, they had kind of the smaller hole in the middle. It was a 12-inch diameter. 12-inch diameter. So that would be then a 6-inch radius, right? 12-inch diameter record. Okay. If I'm taping ants down at 1 inch, so here's the first ant. Okay, I guess we should make him red. Okay, there he is. He's 1 inch away. I want to figure out the linear velocity. So as that thing spins at 78 RPMs, he's going round and round and round. He's going to puke his formic acid, right? But how fast is he going? Okay, so if that tape were to break off, he would fly off the record at that tangential velocity. So V equals R omega, right? So let's plug in. That's 1 inch times, what is omega? Very good. 78 RPM is a measure of angular velocity. Okay? I want my final answer to be in feet per minute. This is in revolutions per minute. So because I'm going to do 3 different calculations, here's what I would recommend. Let's go ahead and convert 78. You want to write it like this now. Revolutions per, that's like 1 minute, right? Instead of 78 RPMs, the horizontal division bar is where the per comes from, right? That's the P. So write it as 78 revs over 1 minute. And let's just convert it. The time unit is fine. We want our final thing to be in feet per minute, so the time unit is good. We just need to convert from revolutions to what? Radians, thank you. Anytime we're dealing with lengths or distances, okay, 1 inch, 2 inch, 12 feet, whatever, and we're talking about rotation, we have to convert it to radians because it's unitless. So revolutions and rotations and degrees and cycles, those are all specific units. They all have to be converted to radians. So 1 revolution is how many radians? 2 pi radians, okay? Now, if you want to multiply that in there with the pi, which is going to make it an ugly decimal, you can. So you have 2 options. You could just say 78 times 2, right? That's 156. You all knew that without the calculator, right? You could call that 156 pi, okay, 156 pi radians per minute. And the benefit of that is you don't need to store anything, do you? Because pi has all the decimals right there, boom. If you wanted to type the pi into it, you know, times pi, that's fine too, but now there's a little bit more work for you, okay? 490.088. You would still need to tell me in 3 decimals. 490.088. 490.088 radians per minute, okay? But if that's the one you're going to use, now that's not exact anymore, so guess what you need to do with your number? You need to store it. Store it, and I'll store it as alpha A again. Okay, I didn't need what A was before, and there it is as A. Now, if I stored it as A, I'm coming over here, and I'm going to call this A as a reminder. So this actually could be useful because now when you're going to be calculating, you don't have to type in 156 second pi. You can just hit alpha A, right? And you know it's going to be the same number. All right, so let's come over here, and here's the benefit of storing it as A, okay? If you tell me on your paper that it's equal to A, then you can actually, in your intermediate calculation, just write it as A. I would be fine with that as an intermediate calculation. It indicates your method perfectly, and that would be radians per minute. So let's check the units real quickly. Inches times radians per minute gives us units of what? Inches per minute. Ruh-roh. We wanted our answer in what? Feet per minute. So there you go. Yeah, you can either immediately just say, oh, 1 inch, I know how many feet that is. Or, before we go to the calculator, that's like 1 inch over 1. Let's just convert that to feet. We want inches to divide out. We want feet to appear. What's the conversion? 1 foot is 12 inches. And notice now your inches divide out. So you could do it like that with the actual conversion factor. Or you could just realize, oh, I want it to be in feet. Well, how many feet is an inch? It's 1/12 of an inch. So you could have just put like a 1/12 right there, 1/12 of a foot. Whatever, however you want to do it. Stoichiometry is beautiful. So now what units are we left with? Feet times radians is feet divided by minute. We get feet per minute. Perfect. Okay, so now we go to the calculator. We don't have to worry about the ones. So it's just going to really be A, which is 156 pi, divided by 12, right? Alpha A divided by 12. Totally awesome. And there it is, 40.840 feet per minute. That is that ant's linear velocity. It's traveling in a circular path, but if it were traveling in a straight line, in 1 minute, it will have traveled 40 feet. It's exciting when you travel fast in a straight line. It's more exciting when you travel along a curved path because then you're feeling the force, the centripetal force trying to pull you off. You feel the G-forces, okay? Okay, same record. It's still spinning. I didn't stop with 1 ant. I had pretty much infinitely many ants. So now I'm taping one 3 inches away. So here's 1, 2, 3. There he is. Tape him down. Here's the sticky tape, okay? Tape him down like that. I'll draw the tape this time. He's 3 inches. So here we go. V equals R omega. Well, we need it to be in feet, don't we? So you could say, okay, 3 inches is how many feet? It's 3/12, right? Or 1/4 of a foot. I don't care if you do it the same way we did over here, 3 inches and then multiply by 1/12. I don't care. Or if you just say, 3 inches is 3/12 or 1/4 of a foot. That's fine too. And if you don't want to store it as A, that's fine. What's the other version of omega that's still exact? 156 pi. So let's just show that option. 156 pi radians per minute. Again, a real quick unit check. Feet times radian is feet. Feet divided by minute is feet per minute. Everything looks good. Now, how are we going to type in 1/4 onto the calculator? When in doubt, you can either hit alpha y equals and do this, right, with the horizontal division bar. That's a lot safer, 1/4, okay, and then say times 156 pi. That's, what's that? Yeah, you could do it like that, or good. You could do parentheses 1 divided by 4, like that, and then also times 156 pi, which remember for me is alpha a. You're going to get the same answer. Or multiplying by 1/4 is the same as dividing by what? 4. So you could actually just do 156 pi, which is alpha a, and just divide it by 4. Okay? And you get the same answer. Just make sure you type it in correctly. All right, so then we get 122.522 feet per minute. Wow, he's traveling a little faster now, isn't he? Right, that ant is feeling more G-force, okay, as he's spinning around. If you were to straighten him out, in 1 minute he will have traveled 122 feet. It's pretty impressive. All right, and then I'm taping an ant 6 inches out. So all the way out here on the rim, I taped him to the rim. So he's got tape here, and then I wrapped it under the record. It's not just laying flat. It's wrapped. It's coming up on the other side, on the bottom side, wrapped it around. He's not moving. He's trying to, but he is stuck, and he's a-spinning, okay? So let's see if we can figure out his linear velocity. V equals r omega. I encourage you to write that down every time. 6 inches is how many feet? 1/2. But let's say we don't know that. Let's just go ahead and say 6 inches times omega, which as we know is 156 pi radians per minute. And then you're like, okay, that's inches per minute. So again, you can multiply, put that over 1, and you could say, okay, I need inches to divide out, I need feet to appear. 1 foot is 12 inches. And there it is. Your inches divide out, and you're left with feet per minute. So that's another way to do it. As long as you're setting it up and the units work out, you've got it. So let's type that in. That's going to be 6 times 156 times, and again, we don't want pi visible because we're not giving an angle in radians. We're giving a distance per time. So go ahead and multiply pi in, and then times 1, which we don't need, and then divide it by 12. Okay? So that's another way to do it. Boom. And you get 245.044 feet per minute. Yeah, feet per minute. Nifty, huh? Now, do y'all have an intuitive appreciation of feet per minute, how fast that is? No. Y'all, in y'all's experience, have a better personal appreciation for what units of speed or velocity? Miles per hour, right? Because you drive that. So let's do this. Let's call that feet per 1 minute. Instead of saying feet per minute, let's call that feet per 1 minute. And guess what we should do? Yeah, since he's moving the fastest, because he's taped out at the end of the record, let's go ahead and convert him from feet per minute to miles per hour. This is so that you're not afraid of stoichiometry. All right, what do y'all want to get rid of first, the feet or the minutes? Okay, let's get rid of minutes. So I have minutes in the bottom. I need it to divide out, so I need minutes in the top. We want miles per hour, so can we go from minutes to hours? Do we know that conversion? Sure. 1 hour is 60, so 60 over 1. As you do that, go ahead and go divide them out. So now we have feet per hour. So we have our desired time unit of hours. So now we need to multiply by another conversion factor. I need feet to go away. Right now they're in the top, so I put them in the bottom. And I want it to be miles. So put miles in the top. Do we know that conversion? Yes, it's one we should know. Good. 1 mile is 5280. 5280 feet in a mile. Memorize that if you don't have it memorized. 5280 feet in a mile. The feet divide out, and now we're left with miles in the top and hours in the bottom. That's miles per hour. So we know we have it. That's it. That's going to work. So now we just go back to our calculator. Do I type in 245.044? No. No, I don't. But notice it is still there from the previous calculation. So all I got to do then is hit times 60, and it's going to bring it up with all of the decimals, times 60 divided by 5280. Remember, the only time you need to be really careful when you're dividing is when you're dividing by 2 pi. You need to either divide by 2 and then divide by pi, or put 2 pi in parentheses. We should be okay here. That looks like it's okay. We don't need to worry about the ones, and we get that. So, wow. Not as fast, maybe, as we were expecting. I mean, it was traveling, after all, 245 feet every minute, but it only comes out to be less than 3 miles per hour, right? Which, I mean, I've been behind guys that drive slower than that through Land Park. It's really annoying, right? Bless you. It's really slow. Now, it might be slow for us because we're ginormous, but to these even big ants, 3 miles per hour along a circular path, yeah. It's probably not nice of me to do that. It's probably cruel, right? Cruel. But I did it, and it passed the time. And years later, it made for a good biographic problem that was relevant. Yeah, I always released the ants afterwards, by the way, and then I'd watch them walk off, and they kind of wiggled like they were drunk, and then they poof right back in their little ant hole, and then we try to kill them all the time, right? No one likes the ants; they destroy the yard. So, but I did let them go before I killed them, with ant poison. Later I came back. I didn't kill them on the record player. That would damage the record. I let them go. Go back to your go tell everybody what these humans are doing, and tell them that the end is near, okay? Yeah. And they're like, dude, the end is near, but, man, you should hear Michael Jackson's Thriller album, right? Yeah. I lived it, man. Round and round and round we go. Okay. How's that? Y'all feeling better about stoichiometry? It's not bad, right? It's not bad. If you put your units in your intermediate calculations, you can check to make sure that you're going to end up with your desired units. And if you do, you've got it set up correctly. It's just a matter of getting into the calculator. And again, the only real thing I will say about the calculator again is when students divide by 2 pi, they tend to mess that up. So put it in parentheses or divide by them both twice. All right. I think we can do one more example. You need one more example? We'll call it a week? All right. Example 8. So you saw my biographic problem. Now it's time for Mrs. Lincoln's. All right. So here we go. Mrs. Lincoln's vehicle, which incidentally is not a Lincoln. I think it's made by the same company that makes Lincoln. It's the Ford Motor Company. Mrs. Lincoln's vehicle has wheels that are 36 inches in diameter. Mrs. Lincoln rolls on 36s, guys. If she's cruising through Land Park, is she the one? Is she the one in front of me, listening to her Michael Jackson record going 3 miles an hour? No, she's a law-abiding citizen. She's concerned for others. She's not speeding, but she's not annoyingly going slow either. She's driving exactly the speed limit, 20 miles per hour. That's her linear velocity down the road, yeah? Okay? As her tires are doing what? Spinning. Ooh. How many revolutions per minute are her wheels turning? How fast are her wheels turning in revolutions per minute? Revolutions per minute is a type of what? Angular velocity. Yeah, omega. Now, for a problem like this, you could actually use, bless you, the V equals R omega and then solve for omega. Okay? But I think it's a little bit easier if we just do this. Which of these two numbers that are given, 36 and 20, which one of those is a variable that's just specifically something at this moment? Which one of those can change at any time? The miles per hour, right? Her wheels are a fixed quantity. It's her speed that she has control over independently. So if you start with your independent variable, the one that can change, but that is choosing right now to be 20. Let's go ahead and just start over here. Write it down, 20 miles per hour. That is a linear velocity, okay? And you could do this one stoichiometrically. All we need to do is now get from miles per hour to revolutions per minute. I think we could do that. So let's go ahead and do the time first. As George said previously, it's probably the easier one. So I have hours in the bottom. I need to get hours in the top. I need revolutions per minute, so I need minutes in the bottom. What's that conversion? This is, by the way, when you say 20 miles per hour, you can put a 1 there if you want. So the conversion is 1 hour in 60 minutes. So now notice that it's flipped from the previous one, but nonetheless, the hours are dividing out. So we've got our desired units of time. Yeah. Now all we got to do is get from miles to revolutions. Okay? Well, first of all, we're measuring her tire in what units? Inches, right? So the first thing that we need to do is get from miles to inches. Okay? So let's go ahead and do that. Can we go straight from miles to inches? Anyone know how many inches in a mile? Too many. Yeah, let's go through feet, right? So again, 5,280 feet in 1 mile. As soon as you do that, your miles divide out. And now we have feet, so let's convert that. Feet in the bottom now to inches in the top. 12 inches is 1 foot. Okay? So that looks good. So now we have inches per minute. So here's the magical conversion factor. I need to get from inches to radians. But I think I'm going to do this first. I'm going to go to rotations or revolutions. 1 revolution of her car is how many inches? Is it 36? Well, let's think about it. Yeah, it's related to half of it because half of it is 18, and that's the radius. Imagine if you were a point on like a pebble stuck in the tire. As she makes 1 revolution or 1 rotation of the tire, that rock travels the what of that circle? The circumference, okay? 1 revolution is the circumference, which is, again, 2 pi r or pi d. So we could just call that 36 pi. Yes? Okay. So that's the magical conversion that gets us from moving down the road straight forward to rotation. We've transferred it from the street to the tire. Now, if you don't want to call that 1 revolution in the top, you can go straight to radians, right? Because 1 revolution is how many radians? 2 pi radians. You could do that, but guess what? If that's too much, no problem. Let's just call it 1 revolution. Now the inches divides out, and then the last thing I need to do is to get from revolutions to radians. So 1 revolution is 2 pi radians. So again, if you need to take more steps, that's fine. Inch by inch, it's a cinch. You're just multiplying by conversion factors, making sure that what you don't need divides out from high to low or low to high, and what you do want to appears in the right place. Now, with everything divided out, what are we left with? We're left with just radians in the top and minutes in the bottom. That's radians per minute. Is that what we wanted? Oh, I went too far. I'm so used to going to radians because that's what we need for subsequent calculations. But this one specifically said in what? Revolutions per minute. So what can I do now? Go back. Let's just get rid of this conversion factor, and that means that we still have revolutions. All right. So now I'm left with revolutions per minute, which is what I want. So you can find yourself going too far. Usually we want to go to radians so that we can compute something, but in the end it said revolutions. So there you go. So we went too far, but we checked out the units, and it didn't work. So then we found ourselves, we went back, okay? The point I'm trying to make is if you constantly check your units, you'll be fine, all right? So now all we have to do is type it up as we see it, all right? This is where we have to be careful. If you divide by 36 pi like this, divided by 36 pi, that's going to be wrong. Yeah, in parentheses, right? It has to be divided by parentheses 36 pi, or it has to be divided by 36 divided by pi. Either one of those, okay? But that is the number one mistake students make. They get all of this correct, and then they still botch it up because they don't type it in correctly. So Here we go. Ready? 20. We don't have to worry about the ones. That's the identity element. So 20. The next factor has divided by 60. So I got that. The next factor is times 5280. Got that. Okay. The next factor is times 12. Times 12. The next factor is the tricky one, divided by parentheses. That's how I like to do it. 36 pi. Okay. You could also use the horizontal division bars each and every time. And then, of course, you could just put 36 pi in the denominator. So that looks everything that looks like everything except the ones, which is okay. You hit enter, and you end up with an answer of 186.741, 3 decimals. And then, of course, what are the units? Revolutions per minute. So you can write it as rev per minute like that if you want. Or, of course, it's customary to say RPM, right? Like MPH, RPM. We've Americanized it because it's so common. Is that a reasonable number? Yeah, we really don't have a true appreciation for revolutions per minute, but it seems okay, right? It's not like 5 million revolutions per minute, which would be too large, or, even 100,000. And it's not too small like 20, right? So yeah, it's reasonable. It's reasonable. Okay, sweet. So again, to get from linear motion to circular motion, you're going to go by way of the circumference, right? As a tire turns 1 revolution, the car advances down the road the exact length of the circumference, right? If you were to cut Mrs. Lincoln's tires, don't do that, right, and lay it flat, there you go. Okay, as you roll the tire, it lays the circumference right there. And so that is 1 rotation advances the car down the road, the circumference amount. Okay? All right. So this kind of problem, you could have also done it this way. You could have solved for omega and gotten V divided by R, and then plugged in the linear velocity of 20 miles per hour, 20 mph divided by the radius of 18 inches. But that's a little bit harder now to go from miles per hour per inch to revolutions per minute. It's just a little bit more difficult because you really have a complex fraction because you have 20 miles per 1 hour. So that really means you have 20 miles per 18 inch hours, right? And that looks a little weird. And then you'd have to convert that still to revolutions per minute. So instead of doing it that way, I find that it's just easier to start with the speed, okay, which is the independent variable, and just through a system of dimensional analysis or conversion factors, including the magical one, the circumference is 1 revolution, just work your way towards the answer, okay? This problem could be done in reverse. It could be given that her tires are spinning at a certain RPM. How fast is she traveling down the road in miles per hour? Okay, so in that case, you would start with revolutions per minute and then do the conversions and get to miles per hour, okay? I think that's how it is in the worksheet. But it would work out the exact same way, okay? That's it. That's page 3 of 4. We will finish the notes on Monday. We'll be talking about Tuesday. Dang, you're right. Martin Luther King Day on Monday. Yep. So anyway, I'll see y'all at the parade, and enjoy the weekend.